Hello, welcome to another module in this massive open online course. So, we are looking at the Fourier analysis of discrete type signals, in particular the Fourier analysis for discrete time aperiodic signals through the discrete time Fourier transform. Alright, so we are looking at the discrete time Fourier transform for discrete time aperiodic signals. Or what is known as the DTFT, the discrete time Fourier transform. Okay. All right. So, now let us look at the properties of the DTFT. All right, we have looked at the DTFT of a unit step signal. So, the properties of, let us continue our discussion with the properties of the DTFT of any aperiodic signal xn. Now, one of the most fundamental properties of the DTFT is that the DTFT is periodic. Okay. So, DTFT is periodic, and there in fact if you can see x of omega plus 2 pi, this is equal to x of omega. This can be seen as follows: x of omega equals summation n equals minus infinity to infinity xn e raised to j omega n, and x of omega plus 2 pi, this is equal to sum n equal to minus infinity to infinity x of n e raised to j omega plus 2 pi n, which is sum n is equal to minus infinity to infinity x of n e raised to j omega n, x of n e raised to j 2 pi n. This is 1, which is in fact this is x of n e raised to minus j omega n minus j omega plus 2 pi, and this is summation n equals minus infinity to infinity x of n e raised to minus j omega, which is nothing but x of omega. Okay. So, this is basically once again this is x of omega. So, we have x of omega plus 2 pi equals x of omega. Okay. So, the DTFT is basically periodic, and the period is 2 pi, the fundamental period. Okay. All right. Let us look at some other periodics properties. Again, one of the simplest properties which is obeyed by all the transforms that we have seen before, and the DTFT is no exception, is the linearity. That is, if x1n has Fourier transform or DTFT x of omega, x1 of omega, x2 of n has DTFT x2 of omega, then x1 of n, in fact a1 where a1 is a constant plus a2 x2 of n where a2 is a constant has the DTFT, as you can expect, a1 x1 n and a2 x2n. Okay. So, this is a linearity, that is a linear combination of the signals has the DTFT, that is the corresponding linear combination of the DTFTs of the corresponding individual signals. Okay. All right. Time shifting, again another important property. What happens when you time shift a discrete time signal. So, let us say x of n has the DTFT x of omega. What happens when you time shift by n naught? So, we are asking what is x tilde omega, which is summation n equals minus infinity to infinity x of n minus n naught e raised to minus j omega n, set n minus n naught equals m, that implies n equals m plus n naught. So, this is equal to summation n equals minus infinity m, in fact m, the index will be m e raised to minus j omega m plus n naught, which is, if you take e raised to minus j omega n naught outside, you have summation m equals minus infinity to infinity x of m e raised to minus j omega m, and this is x of omega, and therefore, this is basically equal to x of omega times e raised to minus j omega naught, that is your x tilde omega. So, when you time shift, that is basically a modulation in frequency. Multiplied by the complex exponential e raised to minus j e raised to minus j omega n naught. So, x of n minus n naught has the DTFT x of omega e raised to minus j omega n naught. Okay. Similarly, we have frequency shifting. Now, in frequency shifting, again one can derive this similarly. Xn, let us say, has Fourier transform x of omega, then e power e raised to j omega naught n, that is e raised to j omega naught n xn, that is a modulated signal. Modulation in time leads to a corresponding shift in frequency. So, e raised to j omega naught n xn, e raised to j omega naught n xn, that is a modulation in time, because you are multiplying it by a complex exponential of frequency omega naught, and that in the frequency domain leads to a shift in the frequency by omega naught. Okay. So, this is modulation in time. Implies a shift in the frequency domain. Okay. Conjugation, when you have xn conjugate, that is xn has DTFT x of omega, then x conjugate n has DTFT x conjugate of minus omega, and therefore, this naturally implies if xn is real, then we have x of n equals x conjugate of n, and that implies the corresponding DTFTs are equal, that is x of omega equals x conjugate of minus omega, and this is something that we have already seen before, that is for an even that is for a real signal x of omega, the DTFT x of omega is basically x conjugate of minus omega. So, the magnitude spectrum is an even function of omega and the phase spectrum is an odd function of, okay. All right. Time reversal, again similarly one can look at time reversal. If xn has DTFT x of omega, x minus n has DTFT, well what is the DTFT? That would be x tilde omega equals sum n equals minus infinity to infinity x minus n e raised to minus j omega n equals summation setting m equals minus n, that would be minus infinity to infinity x of m e raised to j omega m, where m equals minus n, and therefore x tilde minus omega equals summation m equals minus infinity to infinity x m e raised to minus j omega m, that is x of omega. So, we have x tilde minus omega equals x of omega, which implies x tilde omega equals x of minus omega, okay. So, basically x of minus n has the Fourier transform as the DTFT x of minus omega, okay. So, x of minus n has the DTFT x of minus omega, all right. And another interesting property is that of time scaling. Now, time scaling is interesting because it does not directly follow from the, and this is a very interesting property because this is one aspect which does not have a direct, which does not directly follow from the continuous time. So, one would be mistaken if one would substitute directly the result from the Fourier transform of a continuous time signal, and the reason is as follows. So, time scaling caution is important note, not, so while most are similar to the continuous time properties, is not similar this is not similar to that for continuous time signals. The reason is as follows, that is, if you look at a continuous time signal, then you have x of a t has the Fourier transform, that is, if x of t has the Fourier transform x of omega, then x of a t has the Fourier transform 1 over magnitude of a x of omega over a. This is the result for time scaling, okay. However, this is not true for discrete time signals in general. However, not true for discrete time signals, DT signals. That is, if you have x of n has the DTFT x of omega, then x of 2n will not have the DTFT half x. This is not true in general. This statement is not true. Okay, this is not true. This is not true in general, that is x of 2n. If you shrink the sequence, that does not have, that is I cannot use the formula 1 over a, 1 over magnitude of x of omega over a, that is I cannot get the DTFT by 1 over by half x of omega divided by 2. That result is not true in general. However, the following result is with this, for the following result is true, that is if I define a signal x m of n equals for any integer m x n over m, if n is a multiple of m, that is if n equals k times m, okay. If n is, that is n is divisible by m, equals 0 and not equal to k m. For instance, for example, x of 2 of n x of m equals x of that is basically equals x of n by 2 if n equals even, and 0 if n is odd. Let us consider for instance, okay. Okay, and for instance, this signal can be visualized as follows. Let us take a simple example. Let us say I have, this is x of 0, this is x of 1, this is x of 2, x of 3, this is x of minus 3, and then if I consider the signal x 2 of n, which is basically so x 2 of 0 is simply x of 0, x 2 of 1, because 1 is not a multiple of 2, this is 0, x 2 of 2 is x of 1. Okay. So, x 2 of 2 is x of 1. Similarly, x 2 of 3 is 0 and x 2 of 4 is x of 2. Okay. Similarly, on the negative axis, okay, this is x of n. So, you are interspersing, so you are inserting zeros in between. So, first thing realize is basically you are inserting zeros in between and you are spreading the signal out, alright. So, x 2 of n, x 2 of 0 is 0, x 2 of 0 is x of 0, x 2 of 1 is 0, x 2 of 2 is x of 1, x 2 of 3 is 0, x 2 of 4 is x of 2, and so on. So, you are spreading the signal out and basically you are inserting zeros in between. This is known as upsampling. In fact, this is known as upsampling by a factor of 2. Okay. So, this operation is basically termed as upsampling. In fact, this is equal to upsampling by a factor of, this is upsampling by a factor of 2. This is upsampling by a factor of 2. Okay. Now, when you upsample a signal, that is x of n, the resulting Fourier transform is x m of omega. That is, if x of n has the Fourier transform x of omega, then x m of n has the Fourier transform x m of, that is, in the frequency domain it shrinks by a factor of 2. So, you have x of 2 of omega, that means what was at 2 pi comes to pi. Okay. So, that can be seen as follows. So, x of omega is periodic. Let us try to plot a periodic, let us plot a periodic DTFT first. Okay. So, this is, let us say, so this is minus pi to pi, this is 2 pi, 3 pi, minus 2 pi, minus 3 pi. So, this is x of omega. Now, x 2 of n will have the Fourier transform which looks something like this. So, this is like, so this is your x 2 of omega, which is the DTFT of x 2 of DTFT of x 2 of n. So, that will look something like, so you will have basically at so this will be pi by minus pi by 2 to pi by 2. What is at 2 pi will come to pi. So, what is at, so at 2 pi you will have what is at, so you have something that looks like pi by 2. So, at 3 pi by 2. So, this is at pi 3 pi by 2, at 2 pi you will have what is pi pi by 2 and so on, and similarly here you will have something that is and so on. Okay. So, this is basically your x of 2 omega, and remember this is x of basically 2 pi. Okay. So, what is at 2 pi will come to. So, this whole spectrum basically shrinks, and what happens is, as a result of that, you can see you have replicas of the same spectrum. If you look at the minus pi to pi spectrum, you will have a replica. So, what this is basically, if you can see this, it is a replica of the previous copy of the previous signal. Okay. So, you have replicas of the original spectrum in minus pi to pi. And you can see that the number of such replicas is equal to the upsampling factor. So, if you have upsample by a factor of 3, then you have 3 replicas. One is the original, and then you have 3 other replicas. If you upsample by a factor of 4, 4 replicas. Okay, 1 original and 3 other replicas. So that is the interesting aspect of this, that is upsampling. Alright. Now, now when you downsample, there is the opposite of upsample, that is you scale down the signal of time domain. It is slightly more difficult to derive the Fourier the DTFT of the resulting signal, because you can see that results in a loss of samples. When you shrink the time domain signal, unlike in a continuous time signal, when you shrink the time domain signal, for instance, if you shrink it by the factor of 2, take only the even samples, then it means basically the odd samples of the signal have to be removed. So, there is a certain loss that is occurring when you are downsampling, and therefore, the DTFT is not, it is not straightforward to derive the DTFT in such a scenario. So, basically one has to realize that the result for scaling in the continuous time does not hold in general for a discrete time signal using the DTFT in the context of the DTFT, that is the discrete time Fourier transform. All right. Okay, again duality, that is another interesting, very interesting property. What happens to duality? And this is also very interesting because we see in the continuous time, if you have x of t which has a Fourier transform x of omega, then we know that capital X of t has the Fourier transform 2 pi x of minus omega. In the context of a discrete time signal, again it is slightly complex. Now first, so let us say we again ask ourselves this question, x of n has the DTFT x of omega, what can we say about x of omega? Well, first realize that x of t is a periodic signal, that is capital X of t is a periodic signal. And this is because capital X of omega is periodic. So, we have x of t plus 2 pi equals x of t. So, this is the fundamental. So, this is a periodic signal. Naturally, when we have a periodic signal, we cannot use the continuous time Fourier transform, but we have to look at the complex exponential Fourier series, and that is going to be related to the that is going to be related to the discrete time signal xn. How is that related? That is not very difficult to see. If you look at x of omega, we have x of omega equals summation n equals minus infinity to infinity xn e raised to minus j omega n, which means now if you replace omega by t, we have x of t equals summation n equals minus infinity to infinity x of n e raised to minus j omega t, and if you replace m equals minus n, if you replace minus n or if you replace minus n by m, then you have m equals minus infinity to infinity x of minus m e raised to j, I am sorry, this will still be e raised to j, sorry, this will be e raised to minus j n t. So, this will be e raised to j plus n t or e raised to j m t in fact. Okay. And now you can see here we have the fundamental frequency omega naught. So, we have the time period t naught equals 2 pi, the fundamental time period, which means the fundamental frequency omega naught equals 2 pi by t naught, this is equal to 1. So, I can denote omega naught by 1 and I can write this as summation m equals minus infinity to infinity x of minus m e raised to j omega naught or e raised to j m omega naught t, where omega naught is equal to 1 and that is the fundamental frequency. And now you can see we have the discrete time, we have the complex exponential Fourier series for x of t. So, I can write it as, just going to write it clearly, e raised to j omega m naught t, and what this is this is a, now you can see this is the complex exponential Fourier series, because you are expressing x t as a linear combination infinite number of complex exponentials at the fundamental frequency omega naught and its harmonics. So, this is the complex exponential Fourier series, and these are the x minus m is the coefficient of e power j m omega naught t in the complex exponential Fourier series. So, basically you can say x of t has the complex exponential Fourier series given by x of minus m. That is the duality result for the DTFT, because the asymmetric nature of the DTFT, when you take the resulting signal in time, that is a periodic signal, okay. And in fact, so the duality result, the complete result is x of n has here the top equivalence is in terms of the DTFT, and the bottom that I am going to write now, if you look at the signal in time, it is naturally going to be a continuous time signal, because x of omega is a continuous time signal, but it is going to be a periodic signal x of t, and this equivalent is in terms of the complex exponential Fourier series x of minus n with the fundamental period t naught equals 2 pi, fundamental frequency, linear frequency f naught equals 1 over 2 pi, angular frequency omega naught equals 2 pi f naught equals 1 radian per second, and this is the result. This is basically the result for the duality of the DTFT. Duality of DTFT. All right. So, basically that completes several properties of the DTFT, starting from the simplest properties, linearity, time shifting, modulation, etc., and finally we have looked at upsampling of a discrete time signal and also the duality property for the DTFT, that is the duality property for the DTFT of a discrete time aperiodic signal. All right. So, we will stop here and look at other aspects in the subsequent modules. Thank you very much.